Sorry, Bhutan, the line disconnected. So let me summarize this. So this piston cylinder arrangement. So intake, I just put here from top dead center to bottom dead center, intake of fresh air. So of course after that the compression stroke is there. So to make this air compact, before energizing, I did not put that. So you have intake, then your power stroke. After that, exhaust. So you can see that intake volume, once the air sweeps in, and the exhaust, that is air sweeps out. So these are the same. So that's why it is called control. It's constant volume here. And of course, when it comes to intake, you have ambient temperature here. Exhaust has little high temperature, means you are releasing energy. So okay, because intake, if I put here, intake has lesser energy, lesser energy content, compared to exhaust. Okay, means air sweeps out after the power stroke. Okay, so the intake has lesser energy content compared to exhaust. So means exhaust means we are releasing energy more than what we have taken from the ambient. So that's why. So this is related to Q out. So this is related to Q out. Okay, in our case, so you have Q out. Okay, and that is of course we mentioned not as out but Q loss. Out is loss. So that is the reason. So constant volume, heat rejection to the ambient or to low temperature reservoir. So this is taken place in piston cylinder mechanisms, okay, which are relevant for Otto cycles, diesel cycle, and dual cycle. Okay, that is what in summary. So if you ask to explain this in Otto cycle, diesel cycle, and dual cycle, so this constant volume heat rejection, if you are asked to reason out, so you can say that it's because of this solution arrangement or this piston cylinder arrangement. So sweeps in and sweeps out, same volume equivalent to the swept volume, or the swept volume, that is the volume between TDC and BDC of this piston cylinder arrangement. Okay, that's right. So later we will look into more. So that's how the Q loss is taken place at constant volume. Okay. So I think this explanation is same volume of air, intake and exhaust, sweeps in and out, but at different energy levels. So sweeps in has lesser energy, or out or exhaust has more energy levels, more energy compared to in. Intake. Okay, so that is the reason. So let me organize it. So that's the reason why constant volume heat rejection takes place in these three cycles. I believe you have some better clarification now because of this. Okay, you have a better clarification. So we have reasons. So then let me take the other one. Constant pressure, heat rejection. Okay, the same applies. The same applies. But at this case, not like this. Because the pressure dominates, high pressures. Okay, quite high pressures. So once the pressure dominates here, okay, from, you can see from 4 to 1 heat rejection. So this is taken place at ambient. Okay, so there are no valves, so those are something like open flow systems. Okay, that's why you have constant pressure, heat rejections. So here the reason is no valves for maintaining strokes in, no valves for maintaining strokes as in piston cylinder arrangements. Piston cylinder arrangement, there are valves, but here what you have is there is a continuous continuous. There's a continuous flow through the components, namely you have compression, combustion chamber, okay, you have compression, combustion chamber, and turbine. So after turbine, it's leaving for exhaust. So in short, this is all the components are considered open. Since it's a complete system, we will say it as subsystems. Okay. All the components are considered subsystems. So in and out, in and out. So if I put that here, this is the cycle. So it's open. In, out from compression. In, out from compressor goes to combustion chamber in. Combustion chamber out goes to turbine. Turbine out goes to this low temperature reservoir. Okay, low temperature reservoir. So that's how it is. So this is the justification. Yes. Components. And the pressure dominates in the flow system. The pressure dominates. Okay, so I just put this separate here. This is some practical sense. So high pressure, exhaust also high pressure. So again, if I take this, not about gas power cycles. Yeah, of course, all common. No? Yeah, we'll put this way. Not only for this. So QL losing to ambient. Okay, or that is reservoir of low temperature. Same way, because of the continuous fuel supply. Fuel is a very dense source of energy. So at the combustion chamber, it's continuous. So this Q in can be considered something like receiving energy at high temperature. It is something like reservoir of high temperature energy. course, that's how you can consider this. Means you need to have a continuous supply to operate this cycle. So it is something like a reservoir effect is there. Yes, that's how it is. So you have two reservoirs, low temperature, high temperature. So you are reserving from high temperature reservoir and losing to low temperature reservoir. And the balance, of course, the purpose is to deliver some work, W net. Okay, so you can have an energy balance as well. So this is applicable to gas cycle and this 3 gas turbine cycle and of course this power cycles, all the power cycles. So once you see the graph, you can recognize this. Okay, all the 4. This is the situation. Okay, even for steam power plants, this is the same. So this is a reasonably good model that you should understand. Yes. So from the working fluid, heat, of course, the higher thermal energy, higher level, receives by this and then deliver work and the balance or the loss, there is a loss, obvious loss, that is transfer into this low temperature reservoir. Okay, quite interesting. So that's how it is. So that is about this constant volume heat rejection and constant pressure heat rejection. We talk about this. So no TS diagrams yet. Now we will be looking into the TS diagrams. Quite straightforward. Quite straightforward. First, we will look into our Otto cycle. Otto cycle, you are considering only this main 4 diagrams, main 4 processes. So intake and exhaust here is not shown in the standard Otto cycle, but in the air standard, means when you are using air, you have to have this too. Okay, and that is fine. So later we will talk about this. So Otto cycle, TS diagram. From the previous notes, I'm going to refer here. Yes, this one. So, yeah, here you can see the TDC and BDC, top dead centers and bottom dead centers. Somehow, here TS of TS diagram of Otto cycle. So Otto gas power cycle, then it's more. Yes. clear. So 1 to 2 is compression. Isentropic. You know that the best compression possible. No entropy change. So 1 to 2, constant entropy. See, right side is TS diagram. So whatever available entropy at 1 remains as the same at the end of the process 1 to 2. This compression means W in. After that, your constant volume heat additions. Of course, you have compact. See, pressure rising from 1 to 2 during compression process at 2 higher pressures. When heat is added by means of combustion due to spark. Okay, so the spark ignitions, you can see at the constant volume pressure rise. So when energy adds from 2 to 3 means entropy rises. When energy receives by the system means, let me explain what is there. Let me explain what is there. Always remember working fluid. So here compression, it's the working fluid. Okay, it's a working fluid. Keep it in mind. Okay, it's a working fluid. Just put aside. It's a working fluid again. Keep it in mind. Energy addition to this working fluid. Or we call it gas power here. So when this working fluid receives energy, okay, entropy level increases. That's why 2 to 3 entropy level increases. See, left PV is the ECA1, 2 to 3 constant volume. So in TS 2 to 3, you just follow the trend, okay? So there is an entropy increase. And obviously temperature is rising, that is natural. Okay, constant volume, heat additions, okay? Then 3 to 4 is the power delivered by this working fluid through this piston cylinder arrangement, 3 to 4. So isentropic expansion. So 3 and 4 constant entropy, 3 and 4. So expands, work out. So 3 and 4. Obviously at 4, temperature is higher. Okay. Temperature is higher and S3 and S4 are the same and you just say 4 to 1 here. Okay. This is taken place through ambient. Okay. Taken place through ambient. Just releasing air, releasing heat somehow by releasing exhaust and taking fresh air. The reservoir of low temperature receives energy same as what this cycle released to the reservoir. Okay, this is constant volume heat rejections. So basically you should understand this connection. So in the exams, for given PV, if we ask for auto cycle to sketch, just do the sketch diagram of TS, you should be able to do this. Okay, You should be able to do this. That's why it's important. Okay. The next we will look into TS diagram of diesel cycle, diesel gas power cycle. So in the exam, instead of diesel cycle, I may put diesel gas power cycle. Okay, diesel gas power cycle. So let me take from the previous notes. Okay, that's why it is related with piston cylinder arrangements. So let me put this diesel gas power cycle, and even I will put our this diesel cycle is the compression ignition. Okay, so you consider only this main for compression, energizing or combustion, and work done and released to the low temperature reservoir. So these four are the processes in this cycle of the main one. When it comes to air standard, you may have other two as well, intake and exhaust, but don't worry about this. So you can see 1 to 2. In PV diagram, it's the compression. Isentropic is the ideal reversible adiabatic we call. I think we have explained this. Reversible adiabatic means no heat loss, and also it is reversible 1 to 2. So 1 and 2 having the same entropy. And during the compression, when the pressure rises, the temperature rises as well. Okay, based on the gas behaviors. So when no heat losses, when you compress it, temperature rises. Okay, it's a simple common sense you can use for this. Even no need to use equations. Okay, then for this case 2 to 3, compression ignition or constant pressure heat addition. Yes. When the same way as here you have to think of the working fluid. That is very important. Okay. This piston cylinder arrangements are working on facilitating or supporting this working fluid to perform this work out by receiving thermal energy, and of course there will be a loss. Okay, there will be a loss as well. Nice to put this picture also. Side. So not relevant for TS, but it's for your memory. So 2 to 3, energy additions to working fluid. Definitely based on the entropy definitions, when energy being received, entropy rises. Here, of course, temperature also rises, because once energized, there is a temperature rise. So temperature and entropy rise. See, this direction, temperature goes high, this direction, entropy goes high. And the working fluid receives energy. Then 3 to 4, constant entropy expansion, like this. Isentropic expansion. This is W out. So this W out is bigger than this W in. Okay, so you cannot judge by using this line. No such thing. So constant entropy, isentropic expansion. Then 4 to 1 is, of course, you are releasing energy somehow with the exchange of atmosphere or ambient or low temperature reservoir. There you can consider dropping of entropy. Means the entropy at 4 and entropy at 1. There is a relative difference. So this is how this can be connected, 4 to 1. So Q in at higher increasing entropy levels, Q loss. So here mentioned as Q out. That is okay. Q even I mentioned as Q out. But it's a loss. Okay. For in this model, it is loss. Secure loss when it comes to model. It's a loss of energy, but it's out here. So again, you should be able to justify this. Okay, don't think of complicated analysis, but the basic understanding of this is very important. Okay. Yeah. Yes. Then we will look into the dual cycle. So dual gas power cycle. In the dual gas power cycle from the previous notes, I think I have sent you the notes, maybe if not, let me send it. Dual gas power cycle. That is, in our case, see the dual cycle here. Dual cycle. Okay. So again, you can see the same 4 processes. TS changes. The same processes TS changes. So 1 to 2, isentropic compression, constant entropy. 2 to 3, constant volume, heat addition, anyway entropy rises. 3 to 4, constant pressure, anyway entropy rises. See. After that, 4 to 5 is isentropic expansion, where the work is out. Oh, that is W out. 1 to 2 is W compression. Okay. And somehow 5 to 1 That is the constant volume heat rejection through the exchange of intake and exhaust through the atmosphere. Okay, so that's how it is. So I hope it is okay. So this is TS diagram of dual cycle or dual gas power cycle. So then we can look into the TS diagram of AR cycle as well. Okay, TS diagram of AR cycle. AR means not to say just AR, for this turbine engine no power plant. Okay, so Britain gas power cycle law. This is turbine engine or power plant. Even in aircrafts, that turbine engine, they call it power plant. Turbine engine or turbine power plant, okay? Or turbine power plant. Then it's more clear. So let's take that diagram first. Let's draw the TS diagram, okay? T-axis, vertical. Then we will go for the S-axis, okay? And want to say, okay? So I will draw like this. Want to. Want to. One, why want to like this? entropy. Okay, I will put S. Temperature. Okay, temperature, and it is more appropriate for TS diagrams. Temperature in Kelvin. Okay, temperature in Kelvin. So 1 to 2 is compression, and this is isentropy, constant entropy compression. So your temperature rises during the compression. Okay. Then you have the energizing, constant pressure energy additions. So for sure, at 3, your temperature is at higher levels. See, temperature is at higher levels. And your entropy also at higher levels. Okay, if I draw the lines, see, T2 and T3, you can see at T3 temperature is higher compared to T2. Okay, same way. Entropy here is 3 this way. So your S2 is here, same as S1. So you can see S3 is higher than S2. And T3 is higher than T2. That's how it is. Quite interesting. So 2 to 3, of course, pressure remains, but the temperature rises. So you can have a little sketch. And you can write here. P is a constant, let's say. C, a constant. That is the high pressure side. See, P2 and P3 at high pressure. It's a small c. P is. So the same way you should draw. You no need to remember. But if you understand, you can draw this. Then 3 to 4, it is the reverse of 1 to 2, because isentropic expansion. Okay, quite interesting. 3 to 4, like this. So your 4 will be here. Okay, so this is it. Sketch only, just to understand the trend. Understand the trend means you understand this TS diagram. Okay. Yes. Then 4 to 1. It is constant pressure, heat rejection equals difference. Here even S equal to C, constant entropy. Here again S equals to C. Maybe too much. Too many boxes. This is 4. Okay, good. And even you can mark here. Compression work. This is W. Compression. Compression. Okay. Then your turbine work. W turbine. Yes. Receiving energy. Q in. Q in. Right over here. Q in. Yes. Q in. Yes. Q out or loss. Q loss. We prefer to put dash loss. Of course, that is out. Q loss to ambient or low temperature reservoir. So beta I put dash loss. Yes. So you can simply construct this. Okay. So when you construct this, you can keep in mind, maybe even I can give the same for the exams also. So You can draw this. You can draw this. Because this is, we call, that's why, understanding. Okay? So you cannot do this with memories. But if you understand, you can reasonably explain this. Okay? So, very simple. Still applicable. Okay? Still applicable. And you can write the energy balance. So, energy balance in terms of work and heat interactions in this cycle. Okay? Energy balance, the first law of thermodynamics, that is what is called the energy balance. You have to look into this. It is quite simple. And each relates to the processes. So let's say 1 to 2 is W compression. Then 2 to 3 is QN. Okay. Then 3 to 4 is W turbine. 4 to 1 is Q loss. So energy balance is about this. Okay. Energy balance is about this. Okay. So if you take the energy balance, it is something like your net energy in related to Q in and Q loss. Okay. Q in minus Q loss is the net energy in. Is same as means equal sign. What? Net work done. So W turbine minus W. So this is your energy balance. Okay. This is your energy balance. So you can write this in many ways. So if you can understand this all, okay, understand this all, in the sense the energy balance, this model, this schematic, this diagram, Brayton PV, and this TS, okay, your basic concept of this is done. The same way you can justify the previous ones like this. So think about this working fluid and the mechanical arrangements, that is in auto diesel and dual. It's about the piston cylinder and somehow ignition. Okay, and here of course ignition is there at the combustion chambers, but here it's a compression. It's a same like the turbine opposite, the similar constructions, the combustion chamber and the turbine. Here the compression is by means of, there is turbine-like similar radial blades arranged in little opposite ways. Instead of expanding, this is for compression. Okay, and of course this leads for suction as well. So receiving intake, compress it, pass to combustion, and then expands that energized liquid, energized gas through the turbine. Okay, so that's how it is. So open system. All the components are open flow system. So we have learned about this. Okay, so this is quite good, of course. Very nice arrangement. Yes, good. So overall, this will be done. Yes. So this one, somehow you have to understand this. Same way you can construct any of the TS diagrams by your own understanding. Okay, good. So I believe you understand this. Good. So here, TS diagrams. We have standard cycle, so I will take the item 3 on. Item 2, I have to take a little time. So they are standard. What cycles? Gas power cycles. They are standard. So air standard cycle, we have to understand this. That's very nice. In air standard cycle, a certain mass of air operates in a thermodynamic cycle, where the heat is added and rejection using external reservoirs. Heat is added and rejects. So I mentioned this. See this one. Heat rejection using external. Consider reservoirs. Don't worry about the external one. The reservoirs. Of course, atmosphere is out of the cycle, but through these interactions we take it. The same way, instead of this continuous supply of fuel for the combustion, it is like the reservoir effect. So the simple way of telling is that it's a reservoir. It's a reservoir. So let me take it. This. What this means. Okay. This is the yes. So I will take that wordings as well. This way. So if I take this, the same. So I will mark this reservoir in this way. Let me take now this one. I will put this way. This is we call high temperature reservoir. Of course, that is the temperature at the combustion chamber. Okay, but that's how when it comes to modeling. Okay, when it comes to modeling, it is like this. So this is the reservoir. This is being received from this reservoir. So I will change the color. Like this. So same way, the Q loss. It's a low temperature reservoir. So just to show the low temperature, I will use little light color. This one maybe I will use. Yes, this way is okay. So that's the light. So understand this with this model. Okay with that? Good. So the heat is added and rejected using external reservoirs. And all the processes in the cycle are reversible. Of course, in the previous ones, yeah, I forgot to mention this P equals C. Okay, it's a reversible process considered. Reversible means there is an equilibrium with the reservoir in this case, either low temperature or high temperature. Yeah. So this is very nice. So this is explained, and then if we look into the assumption, the working fluid, you know this, that is air, for air standard, behaves like an ideal gas. Ideal gas means that ideal gas laws I mentioned to you earlier, PV equals inertia null applies. Okay, as ideal gas. I have mentioned about ideal gas earlier. So combustion is replaced by heat addition. So in all the 4 cycles, we consider combustion. So is replaced by heat addition. Heat addition means this way. So let me take this. This tells everything. Okay. No space. Here I can. Here should be okay. And the exhaust process by heat rejection. So these are assumptions. Okay. Of course, all the processes are reversible. Yes. So here, so we will consider these things. And this is quite okay. Oh. So this is the model. Let me take a little space. So air standard. So standard here, of course, with this definition it comes. Okay, this is for the air. Practically, we are using air as the working fluid for all the cases. Good. So that's why I mentioned you already knew. Okay, this one you already knew. So after that, I will look into this. I skip here, network done, and the gas power versus vapor power. You know this. Gas power cycle systems versus vapor power cycle systems. Okay. So if you look into even this one, we talk about this turbine engine. This is a single piece, once assembled. Okay, this is single piece. That's why. So even when it comes to the other cycles, piston cylinder arrangements, you can have as a single assembly. That's why in the aircraft you can carry it. In the vehicle you can have this. So that's why the gas power cycle systems are compact. So that is the advantage of this. You can make it lighter, you can balance it with the application and all. But when it comes to vapor power cycles, okay, vapor power cycles, earlier we have learned about this. Okay, Buddha? So same like steam power plants. If you think about, okay, your basic components you have learned. We have learned about this. After learning refrigeration, we learn about this. Pump, boilers, turbines, and condensers associated with this ranking cycles. We have to discuss this further, not to say discuss, but we have to how to say, since we came to know this, we have to revise this, that's all. This one, when it comes to the designs, it has bigger components and all. So huge that if you see a photograph of or a picture of, let's say, of a steam power plant, it will be like this. This will be, I believe this can be a steam power plant. So let me take, not this one, that is not steam power plant. It has storage, so that is not steam power plant. This components, but finally you can see like that. But of course, to operate this, you have to have nearby water reservoirs, low temperature, means either sea or a big river. That's why in our case, Norachole and all, whatever, when it comes to steam power plants run by coal or whatever, it should be at the seaside. You cannot have this in the land side. So you have to have abundant water source as low temperature reservoir, or that would be the sea. That's why now you can see that heat rejection, because in any system there are heat rejections. Now there is a complaint that because of Norachole, there are temperature rising at the sea at that locality. So that's why that is the low temperature reservoir. So this Q loss is to the sea or to huge, if you have abundant or plenty of water resources, you can use land, or else should be a huge river or sea. So TH, this is from the coal. You process it, you fire the boil. Yes. So you have emissions and all. So this cooling tower, the big one, is for cooling this steam, that is we call condensers. To support condenser, the cooling tower is here. So we have to learn about this as well. Very interesting. So when it comes to vapor power cycle, okay, so this is the gas power cycle system left side. The vapor power cycle system, you have right side here. Okay. And the vapor power steam, normally we use the Rankine cycle. Can you remember Rankine cycle? We have learned. So this will be in the exams with the practical tips and all. So we are not only asking the basics, but some practical sense will be tested. So this is vapor power. So, and the Rankine cycle, as I mentioned, is related to the vapor power cycles. Okay, with the Rankine cycles. So last time we have discussed this, explained very well. So this will be in the exams. So we are asking the basics, and also we will be, basics means you understand. Okay, so we will test your understanding reflections. That is very important. So this is the ranking cycle. Let me put this somewhere, minimizing this. The ranking cycle. So we have learned about this. So here 0 to 1 is the pump. See, you can see pump. 1 to 2 boil, 2 to 3 turbine, 3 to 0 condense. We have discussed this. Okay, so you will be looking into these aspects as well. So compactness. Okay, so this is about the compactness. So I will change this to the gas power cycle, gas power plant, compactness. Okay, overview. So it is something like this. So look into this, and IC engines. You know about this. About TDCs, about BDCs. Okay. About inlet. See, this is the one. Of course, air fuel mixture. Oh, for the compression, it is different. Okay. So air in, let's say, flows through inlet valve and exhaust leaves through exhaust. Okay. So in the mechanisms, of course, you know about the piston cylinder and this crank mechanisms, okay, with the connecting rod and all. You have the basics, so later we will discuss this and this. Cylinder and piston arrangement, you have TDC and PDC. Okay, and we talk about suction power, okay, exhaust intakes, strokes. So stroke is something, the sweeping of this piston. So this is TDC and BDC gap. Okay, so bow is the size, the diameter of the cylinder and all. So clearance and the compression ratios, clearance volume and the displacements of the complete engine is related to the cylinder, individual cylinders, and this swept volumes of each cylinder. Okay, so this one we will discuss after it. Right? So you should look into this as well. So today I have to stop the class a little earlier due to some unavoidable, okay, reasons. So we have done something good. So next day will be the revision. Next day will be the revision. I will start revision starting next session. Even in between, I will try to take revision sessions, because before that, make sure you know these things. So gas power cycles. Cycle engines. Okay, overview. So understanding TS diagrams. So this is considered done. Okay. Yeah, standard cycles you already know. Just to mention you the wordings here. Okay. This one is a very basic one, but important tips are there. So next week, so we will understand this. Network done, gas power versus vapor power, and together with this, we are going for revisions. Actually, these are revision sessions I put here. Okay, Bhutala? We will go for revisions and some little analysis, don't worry. So, understand the things we have learned till today. That is very important for technology. Later, we will do the analysis. When it comes to example, even I will post some something like questions, and some questions, both the qualitative means the technical and analytical questions I will post to you for you to work out in return to clarify this subject. Okay. Thank you, Bhutala. So anything, any question before winding up this? Prashna Dina, Bim sir, as usual. Puta terunada kiyabu tika. Hello? Lamenta hinwada terunada. Kohomada. Muna Singh, are you okay?
Yes, sir.
Okay, okay, good, Puta. Also, I saw Rahim. Puta, you just signed
Yes.
out. Yeah.
Yes, sir.
Yeah. So actually, this subject understanding is totally with you. So I am supporting this way as a support for your thought process. Yeah. So even our side as lecturers, we have limitations. So your side commitment is equally important as our side commitments, Putal. Yeah. So if you have no intention to understand this, you will not understand. Yeah. So simply listening is not enough. You have to have some attention, imagination, and explore something with some technical aspects, and because engines and all is nothing new to you. So with some imaginations, you have to match this knowledge with your understanding. That is very important, Puta. Okay, that is very important. That's why this responsibility is among both the lecturers and the students. Thanindu Tirunada Buddha, Deshan. Okay, good. Wow. Definitely you should expect minimum two questions from gas power cycles. Okay. I will try to put 8 questions, 2 from gas power cycles, and also from vapor power, another 1 or 2. Okay. Refrigeration, another one. And the basics of open flow systems, closed systems. and the first law of thermodynamics, second laws about the entropies, and little bit about the gas laws. Altogether there will be 8. But this is not calculations mainly. There can be calculations, but in our case, okay, calculation is not the number one. We will test your understanding. Okay, Budala? So you can write plenty. So there will be 8 questions. Out of that, you may need to answer only 5, maximum 5 maybe. So you have choices, and we will make it very nice. It's quite standard. And upfront, I give you notes. So wherever difficulties, you can refer the notes, and even there are better presentations you can see in the web, because mostly it's a self-studies, and other than that, of course, my videos also, I would say it's effective for you, so you can look into those as well. Okay, Budala, so I think time has come to seriously study, because exam will be somewhere at least by end of March, let's say, at least by end of March. So don't wait till uh, it's nearing the exams. So this is the time you can finish completely this studying of thermodynamics. Okay. Yeah. So we will go for the revision examples, model question papers and all. Don't worry. Exam is quite easy, but it will test your understanding. What we have discussed today will be in the exam. Justifying the TS diagram, about this modeling. Yes, very interesting, these concepts. Yeah, standard cycles. Yes. About the engine mechanisms, high and low temperature reservoirs. How do you understand this? Connecting of Q out or the Q loss through the environment. So nice. These things. And also, of course, constant volume heat rejection. How can this be when it comes to this cycles? So in actual applications, there can be little variations. Don't worry about this. So quite interesting. Okay, very good. So that's all. I have to stop the class a bit early. And I did a mistake earlier that I put here constant volume for Brayton. It's a big mistake, but it was corrected here. So please take note. Only auto, diesel, and dual cycles have constant volume heat rejections. Brayton is constant pressure, and we have justified those as well. So why these heat rejections, either constant volume or constant pressure? So try to understand those and try to get justified to you. If you understand technology, you can outline lot of solutions. That's the point. Okay, so we should move beyond the books, and we should do something with this subject. We can move forward. So manufacturing students are meeting in the next semester for advanced thermodynamics or applied thermodynamics. So when it comes to applied thermodynamics, we will go for more analysis and even for some innovative approaches and maybe some project related things as well. But mechatronics is with us, so it's our responsibility to give both of your batches the very basic elemental thermodynamics seed. Okay, thermodynamics seed to the fullest for you to move forward. Even though mechatronics are not following applied thermodynamics, this thermodynamics is extremely important subject. So without this, it is very tough to move for anyone, because thermodynamics is almost everything. Yeah. So So thank you, Buddha. So be serious on this subject and try to complete this. So today I will upload the video and the notes as well for you to go through. So immediately afterward, I will post this. So Saturday we will be discussing similar ones with B2 batches, and we will be posting that as well. There can be little extra knowledge or different knowledge. So there can be little deviations when we share with different batches. Not purposely, but that's the way it is happening. So thank you, Bhutana. Take care, all of you. So uh, be ready, get ready for the exams and don't wait for last minute. So that's all from my side, and any concerns you can raise, you can email or anything. Okay, Buddha. Thank you very much then. I believe no questions. So take care all of you. Bye then. Bye.
Thank you, sir.
Okay, Buddha. Bye.